Hello physics students, this is Dr. Brenzi and this is the video for lesson 6.1.4. Our objective for this lesson is that we're going to be able to calculate velocity, angular momentum, and the energy of an object in a circular, or in the case of AP, an elliptical orbit. I want to start this class off by talking about Isaac Newton and one of probably his most famous discovery, and that is the discovery of universal gravity. And I told you that Newton came up with the formula for universal gravity, and that's why we call it Newton's law of universal gravitation. Newton's law of universal gravitation, right? Well, here's the experiment that Newton thought of, and this comes, you may have heard of Newton's story where the apple fell on his head. Well, it probably didn't fall on his head, but he probably saw it falling on the ground, and he started to think, it doesn't matter how far this apple falls from the tree, it's still attracted to the ground. And then he started thinking about longer distances and started thinking about whether or not these gravity goes all the way out into space and is the reason that the moon is attracted to the Earth. Well, he figured this out by doing what's called a thought experiment. And a thought experiment is like an experiment you do in your head. So Newton thought up of a cannon, a really, really strong cannon that can fire a cannonball really, really fast. Okay, so he thought, well, if you start off and you give it just a little bit of gunpowder, what's going to happen is that the path of this cannonball is going to go some distance and it's going to fall. And then he thought, well, if I do this farther and farther, then the curvature of the Earth is going to start coming into account. And they thought, okay, well, I fire it farther and it does something like this. I fire it a little bit, put a little more gunpowder in it, and it may do something like this. Well, alright, that's kind of sloppy, but let's try that again. Alright, so it may do something like this, and it's eventually going to fall back and hit the Earth. But then he thought, if you fire it fast enough, what this cannonball is going to end up doing, and let me do this in another color, this cannonball is going to keep on falling and falling, falling and falling, but it's going so fast that it's never going to fall and hit the Earth. It's going to end up going around and around and around and around and around and around in a circular orbit. And then Newton thought, wow, maybe this is what the moon's really doing. And then this guy, would actually end up shooting himself in the head because the cannonball's going to go all the way around the world. Well, Newton didn't take into account air drag or things like that, so I don't think the guy was in danger of having this happen to him. But this was Newton's big experiment that he thought to himself. He says, I wonder if this is what's happening to the moon. The moon, I wonder if this is what's happening, is that this, just like my cannonball, the moon is in perpetual free fall. So it's always falling and falling and falling and falling, and it's never going to land because it has enough velocity where it's never going to land on Earth, and it'll keep going around in an orbit. So it was Newton's big, huge idea. So we can think of orbits as a perpetual falling. Something that's going around in an orbit around another body is in perpetual free fall around that latter object. So we can think of the Earth doing the same thing. Now let's approximate the Earth with a circular orbit. Now if we apply what we learned in Unit 5 about circular orbits or about circular motion to orbits, well, we know that there is some force that is pulling the Earth toward the sun, and according to Newton, this force that's pulling it to the sun is gravity. Okay. So the force that's providing the centripetal acceleration of our Earth around the Sun, or any other planet around the Sun, or the Moon around the Earth, or satellites around the Earth, that centripetal force is gravity. So, actually, let me write that in letters instead of symbols. So if we set up Newton's second law that says that F net equals mass times acceleration, well, we know that the net force of the net force acting on the Earth is gravitational attraction of the Sun, so that would be Fg. And then we know that this equals the mass of the Earth, whoops, times A. Well, what is the acceleration of the Earth as it goes around the Sun? Well, we know that that has to be a centripetal acceleration. Okay, and if we go back to Unit 4, we have a formula for centripetal acceleration, and that is equal to v squared divided by r. So if we plug that in, it turns out that Fg equals m v squared divided by r. And now we can use Newton's law of universal gravitation in here. We have big G, big M, little m over r squared. Remember, this is force, so it's squared, equals m times v squared divided by r. Okay, so when you set this up, a few things happen to fall out. We know that there's mass on both sides, so those divide out. And we know that if we were to multiply both sides by r to get rid of this radius, it would turn out that this r would divide out with one of those r's. So now we have g big M over r, equals v squared. So an object that's in circular orbit, whoa, what did I do here? Let's go back. So an object in circular orbit has a velocity equal to the square root of big G times the mass of the Sun divided by its distance from the Sun. Okay. This is a really important formula to remember. That one right there. Okay. So just by using some of our understanding of circular motion and the fact that the centripetal force of the Earth going in its orbit is the force due to gravity with the Sun, we find out that in a circular orbit, our orbital velocity would equal the square root of g times the mass of the Sun divided by the radius. Well, we compare that one that I just came up with, v orbit, is equal to the square root of g big M over r. And if we go back to less than 6.1.3, when we were calculating escape velocities, we found out that the escape velocity of an object is equal to 2 times big G times big M divided by r. Well, if you were to find out, okay, what's the kinetic energy of this object while it's in orbit, you'd have 1/2 mv orbit squared Well, that would turn out to be G times big M times little m divided by R. Oh, divided by 2R, excuse me. And then over here it would turn out that the kinetic energy we would need to escape, 1/2 mv escape squared, well, we figure that out, and it's going to turn out to be G big M little m divided by R, just by plugging it into the kinetic energy formula. So an object in circular orbit has exactly 1/2 of the kinetic energy it would need to escape. Whoa! Yeah, so that's true for all circular orbits, actually. It turns out also, one other thing, is that you can find the total energy of an orbit which is kinetic energy plus gravitational potential energy. Well, we just figured out that the kinetic energy is G big M little m divided by 2R. And then we have to add negative, remember gravitational potential energy is a negative, so we have big G big M little m divided by R. We learned that in a previous lesson. And when you take the sum of those two, you end up with negative big G big M little m divided by 2R. Well, okay. Well, you might have been able to quickly see that this is just the negative of that. So the total energy is E total, and this might look strange when you look at it at first. Total energy of an object in circular orbit is equal to negative KE. Like, whoa, that's really strange, but that turns out to, that's how it works. We're not used to seeing negative signs here and total energy equaling a negative number, but you know, it just tells us that we're in a hole, that we're trapped. We're bound by the gravitational energy, or excuse me, the gravitational pull of the planet. Or actually, in this case, it's the sun. Sorry. Alright, now I want to talk about elliptical orbits. Okay. Now, these two statements right up here are true for both elliptical and circular orbits. So these are true for all orbits. It's true that angular momentum is conserved in a circular orbit, and it's true that angular momentum is conserved in elliptical orbits. Okay. The same applies for total energy, which is kinetic plus gravitational potential. And both of these items are conserved. So, what does that mean for an elliptical orbit? Well, you know already that when you compare a planet at its closest distance to the sun versus a planet that's farthest away from the sun, you know that its gravitational potential energy, UG, is at its lowest when it's closest to the sun, and its gravitational potential energy is highest when it's farthest away from the sun. Well, if total energy is conserved, that means that kinetic energy here at its closest distance to the sun has to be at its highest point, and kinetic energy when it's farthest away from the sun has to be at its lowest. If you happen to know the gravitational potential energy at this point, and you would just need to know the mass of the two objects and their radius, you learned how to calculate gravitational potential energy in a previous lesson. So if you end up knowing that, and you end up knowing how fast this planet is going at this nearest point, you could actually calculate its total energy. And it would have that same total energy no matter what that energy is around the orbit. Okay. Now, the fact that gravitational potential energy only depends on the distance you are away from the sun. That means if you are, say, in this position, and you know the distance from here to the sun, you could actually calculate the velocity at this point because total energy in the orbit is conserved. So when you go to do problems, you can get problems like, say, you know the velocity maybe either here. Whoops, what happened there? You might know the velocity here along with the radius, the distance to the sun here, and you might have to calculate the velocity of our planet, say right here, and you do that by conserving energy. Now, a little bit of vocabulary. I'm not going to test you on this vocabulary, but there are some words here that will help us out. So there is some technical vocabulary for talking about the distance closest to the sun and the distance farthest away from the sun. I didn't use those words in the previous slide, but I will now, and I will in the future, because you never know when you might come across a homework problem or a test problem that mentions one of these words. So the distance, when a planet is closest to the sun, we would say that planet is at what's called perihelion. And what that means is that it is at its closest distance. Para means closest, helion means sun, so closest distance to the sun. Well, when this planet moves to this position in its orbit, it is now at aphelion. And aphelion means farthest from the sun. Okay. Now, when we're talking about orbits around an Earth, like say for an artificial satellite, instead of talking about perihelion and aphelion, we actually talk about perigee. Para meaning closest, G meaning Earth, and we talk about apogee. So sometimes this prefix right here adds an O before you attach the stem. So this is apogee. Okay. And then there are also stems that are less frequently used, like apastron, which means its farthest distance away from a star. So it might be talking about a planet in a different solar system going around a star. And one that you hear less frequently than that is loon, which means moon. So if something were in orbit around the moon, you'd be talking about periloon and apoloon. It kind of sounds strange, apoloon. This sounds like a treat or something like that. I don't know. Anyway, that's the end of the notes for advanced physics. But AP, I have a few more notes that I want to show to you. And advanced physics, if you're really going to stick around, go ahead and do that. So let's talk about elliptical orbits, AP. And ellipses can be classified according to something that's called eccentricity. It's a number, oops, it's a number that describes, you can probably tell, it tells you basically how flat or how oblong the ellipse is. So something that has an eccentricity of 0 is a circle. And then as you get flatter and flatter, this eccentricity increases, but the eccentricity never gets greater than 1. So we can talk about eccentricities that are between 0 and 1. We never get an eccentricity greater than 1. Otherwise, you're no longer talking about an ellipse. You're talking about something else. But I don't want to get into that. Well, the reason I say this is because we can use eccentricity to say something about velocity at perihelion and aphelion. So you have an elliptical orbit here, and it turns out that the distance from the sun to its perihelion, so it's perihelion distance, this distance right here, turns out to be A times 1 minus epsilon. And epsilon is that Greek letter we use for eccentricity. My dog just got up on the got up in the chair, and I gotta kick her off. All right. She apparently is really interested in eccentricity. The distance, the aphelion distance, which is this distance over here, that is equal to A times 1 plus epsilon. And I forgot to tell you what A is. Well, A is the semi-major axis distance. So let me draw this in a different color. So if this is the center of the ellipse, I'm hoping that's pretty close, then this distance right here is A. So you might just want to put over here on the side that A is A is defined as the semi-major axis. All right. Well, it turns out that you can use conservation of angular momentum to figure out a relationship between the velocity at perihelion and the velocity at aphelion. And we can actually do that one on this slide. So angular momentum, L, for a single point mass, well, we know that L equals I times omega, and that I for a point mass, we're going to treat the planets like point masses, is mr squared. And we know that omega at these two particular points, and we can't say this of any other points in the orbit here, but we can say it about aphelion and perihelion, and the reason is because the entire velocity vector is perpendicular to the sun. In other words, there's no radial component for velocity. It's all tangential right here. Whereas if we were at this spot or any other spot in the orbit, we would have a component of velocity, which is again tangential to the line, but there's a component of this velocity that actually points either toward or away from the sun. So I can only make this statement about omega when we're at perihelion or when we're at aphelion, and that is we can use omega equals V divided by R. Okay. So it turns out that this becomes MVR. This only is true at perihelion and aphelion. Now it turns out that if we have circular orbit, then actually this would be true for any position in a circular orbit because perihelion and aphelion are the same. Well, they're actually, yeah, they're the same distance, so you're at the same distance all the way around. And you could use this for circular orbits as well. Alright, so if I conserve this, we know that the mass of the planet times its velocity at perihelion times its radius at perihelion is equal to the mass of the planet again times the velocity at aphelion times the radius at aphelion. The mass of the planet divides out because we're going to divide both sides by m. And we know from the previous slide that I gave to you that the radius at perihelion is equal to the semi-major axis A. Oh, actually, it's not the previous slide. It's this slide. Sorry. So if I replace the radius at perihelion with this term, and then if I replace the radius at aphelion with this term, I get a relationship that looks something like this. And, well, we know the semi-major axes, they are factors on both sides, so they'll end up dividing out. And we get VP, V perihelion, times 1 minus epsilon. That's the eccentricity of our orbit, equals the velocity at aphelion times 1 plus eccentricity. All right. So this relationship will apply between the velocities at perihelion and aphelion. Now, if you were to then use conservation of energy at these 2 points, you could actually come up with the velocity at perihelion and the velocity at aphelion. And it turns out that if you do that, yeah, the reason I'm not going to actually do that on this slide is because it involves quite a bit, oops, not energy, that's energy. It involves quite a bit of algebra. So it turns out that the velocity at perihelion is equal to the square root, I need a longer square root, it turns out to be g times big M over 2 times A. Let me make sure I have that 2 times A part right. Oh, no, it's just A, sorry. Gm over A times a quantity, and for perihelion it's 1 plus epsilon over 1 minus epsilon. Okay. The velocity at aphelion looks very similar. G big M over A, and this will be 1 minus epsilon in top and 1 plus epsilon in the bottom. Okay. Now these formulas look really, really similar, right? And you might accidentally get them mixed up. Well, the thing to remember is that at perihelion, you know that the velocity is going faster. Kepler's second law tells us that. So we would want 1 plus epsilon in the numerator. And aphelion, we're going slower, so we would want 1 minus epsilon in the numerator of our little fraction there. So that's the big way to tell the difference. Okay, so there are some, let's see, what else do I want to talk to you about? There's one other thing I want to talk to you about. The total energy. It turns out that you can calculate the total energy that our planet has at perihelion. And when you do that, you get E equals negative m. Actually, let me do this. It turns out to be, this turns out really elegant, G big M little m over 2A. And this is the total energy, actually, that you'll get at any place in the orbit, because total energy is conserved. So anywhere in our elliptical orbit, you will get total energy E equals negative G m over 2A. Now, if you compare that with our circular orbit, you'll notice that this looks very, very similar. Instead of having our semi-major axis A, we had the radius r. So these are, in a sense, the total energy in an elliptical orbit is the same as a circular orbit with a radius of A, which is your semi-major axis, which is a pretty cool thing to remember. Alright, so if you know the semi-major axis, you could actually compute the total energy that the planet will have anywhere in its orbit, and if you know its radius at any point in its elliptical orbit, you could actually figure out what its velocity has to be at that position, just like you would do with a circular orbit. Okay, that's it for the notes. I know this is a long video, but there was a lot to go through, and orbits are really cool in my mind, so I wanted to show you some of those neat little relationships with energy and radii and all that fun stuff. So anyway, I'll look forward to seeing you tomorrow in class, where we can apply some of this to some physics problems. Take care. Bye. Oh, gee.